So we have the basic sequence of 1 plus 2 plus 3 plus 4 plus 5. And we want to try to figure out the total sum of these numbers. Now, it probably looks easy. You might say, oh, let's just add up 1 plus 2 plus 3 plus 4 plus 5. And yes, then you would get the correct answer. But what if we add larger numbers? So there's actually a formula for this, but I want to figure out how can we actually get to that formula? How can we understand why that formula works and what are its uses for other areas of math? So first of all, I have the symbol over here, a capital sigma, and it basically stands for sum. And we'll check it out later when we're looking at more kinds of different sums. And it's really interesting because if you're in computer science, it works exactly like a for loop. So I think you'll find that interesting if you're taking a computer science course. But even if you aren't, it'll definitely be very interesting. But first off, let's start with these simple sums. So how can we approach this? Well, we know directly that the answer will be 15 because we just have 6 plus 9. But let's say we had 1 plus 2 plus 3 plus 4 plus 5 plus 6 and on all the way to let's say plus 20. Now it gets a little more difficult because we don't have as many numbers. So let's see how we can approach this. Well, the interesting thing is, if we go back to this 1 plus 2 plus 3 plus 4 plus 5 idea, we can notice that 5 plus 1 is 6, and 4 plus 2 is 6, and 3 plus 3 is 6. So it's interesting to notice that if you basically just add the opposite ends of each ring, kind of like this goes here, this one goes here, and then this one goes to itself, you have 6 plus 6 plus 6 plus 6 plus 6. Of course, that may not work so easily because you might say, well, there's only 1 3 over here. We can't do that. So let's see what else we can do with that. But on the same idea, I do want to achieve some sort of equal number on all 5 of these numbers. So let me add a 5 over here because that makes the 6 that we want over here. And then I think you may see where this is going. If we had a 4 over here, we can have a 6 over there, then a 3, then a 2, and then a 1. And now as you've seen, if we add all of these together, we have a 6 in each one of the terms that we've had before. So now we have 6 plus 6 plus 6 plus 6 plus 6. And this is really interesting because based on this, we can now have an easier way to represent this sum. The only problem is we still have a duplicate of that sum. So how do we get rid of that? Well, one easy way is to just divide by 2. We can divide these 5 times 6 over here by 2, and then we'll achieve the 15 that we want. So this is equal to 30. And then we want to remove the original duplicate we have over here. So in order to do that, we have to divide by 2. And we have the 15 that we got before. So now that we've done all of this, let me just erase all of that. So now that we've done all of that, is there a more general way to represent this? Like let's say, or let's try a little more difficult example, just one that's less intuitive. Let's do the sum of the numbers 1 plus 2 plus 3 plus on and on and on, all the way until 18 plus 19 plus 20, as we've had before. So, can we do this the same way? Well, we realize again that if we take like the ring approach from before, then we'll have a sum of 21 on each of its ends. So we'll have 21 here by adding this 20 and this 1. We'll have 2 plus 19 is also 21, 3 plus 18 is also 21, on and on until the center. So, doing the same thing, we add 20 to this side, which we're basically adding the same thing. I think that's the basic intuitive feel you need to get over here. We're adding the same thing to itself, but we're just reversing the order to do so. It's a very creative trick. So based on that, we just add it backwards, and then we'll have the same idea here going on and on until 3 plus 2 plus 1. And as we can see, if we add all of these up, you can just put parentheses to make it easier to understand. We have a bunch of 21s here. 21 plus 21 plus 21 plus on and on and on. It's 21 plus 21 and plus another 21. But now we have to think about it. How many 21s are there in here? It's not as easy as before where we could just see, oh, there are 5, 6s. But now there's actually some number of 21s that is not as easily countable. So how can we tell? Well, one of the basic things we can know is that there's 20 numbers in this set, because if you have a sequence like 1, 2, 3, 4, 5, 6, and it goes on until that some number, it's going to have that many numbers, because imagine you have 20 objects, and as you can see, this is the first object, this is the second object, this is the third object. So logically following, the 20th number will also be the 20th object and will be the number 20. So that means we know that since we're just adding them straight down like this, we'll have 20 21s in here. So there's 20 of these in the bottom. So that brings up an interesting point. So that means this time we'll have 20 times 21 over 2. So since we have 20 times 21 over 2, this looks very interesting. Originally we started with 20 numbers, right? And then we added 1, 21. So we got, let's say the amount of numbers in, or the number of numbers in this sequence was 20 numbers. And remember, the difference between each of them was 1. There's a common difference of 1 between each of these numbers. So let's say this was an arbitrary number n. And then what we did was we multiplied n plus 1. And the way you can think about this intuitively is that, why would it always be n plus 1? Well, you'll have the n at the beginning, and you'll have a 1 at the beginning, you'll have an n at the end and a 1 at the beginning. So essentially, you'll have n plus 1 in each. And as you know, since this one is linearly increasing from this side, and this one is linearly decreasing from this side, you'll keep on having that sum of 21, 2 plus 19, 3 plus 18. So you know that all you have to do to figure out, wait, so why is it n plus 1? Well, you just have to realize that the 20 on the end of this side will add up to the 1 on the end of this side. So if this is n, then it'll be n plus 1, and that'll be our special number over here that repeats. So we have n times n plus 1 over 2. And I think that's a really nice intuitive introduction to this formula, which works for a certain class of numbers. Of course, there's still things you need to do. Like, for example, you need to have this common difference of 1 between each of the numbers. This formula can be applied, but doesn't exactly work for different common differences. You'll have to do some extra multiplications. And I'd like to see if you can figure that out. Try to apply this formula with any sum of an even numbers, like 2 plus 4 plus 6 plus 8. I think that would be interesting if you could figure out how to apply this formula and how it applies to many different other sequences. So try to see where this works. And you can use this logic in many different places to prove different kinds of sums of series. But now I will talk about this little symbol that we have up here, just a basic introduction. So how can we represent this 1 plus 2 plus 3 plus 4 plus 5 here in a better way? Because as you saw, it took a really long time to write 1 plus 2 plus 3, all of these numbers over here. So that's why they made this symbol. They wanted it to be easier to represent these kinds of sequences, but also there are different kinds of things you can write with them that you usually wouldn't be able to do. So, I mean, I like to think of it, because I do computer science, I like to think of it as a for loop. But if you don't know what a for loop is, then I'll just explain it generally so that it's easier to understand. But for computer science students, try to look at it. Why is it a for loop? But for any other students, just look at it generally. So what we want to do is start with a number. So in this case, we have 1. And we want to declare a certain variable for that number. So usually it's named I. So let's put I is equal to 1. So we're starting with the original 1. And let's see, how many iterations of that I do we want? Well, let's represent this first sum over here. We had 1, 2, 3, 4, 5. So that means the first iteration will of course be 1. So we have an I is equal to 1 over here. We also have an I is equal to 2, an I is equal to 3, an I is equal to 4, and an I is equal to 5. So the way to write this is we want to put 5 at the top of our sigma to show that we're starting at 1 and we're stopping at 5. So in this case, we will have, we also need to write what we're iterating, so that'll be I. And in this case, we'll have to go through each iteration and add. So what this symbol is doing is basically a machine, if you think about it. So first it goes, okay, so I start I equals 1. And then I equals 1, so it puts a 1 there. And then between its rotations, between its iterations, it'll add a little plus sign there once it completes a task. Next, it'll go, okay, so now I have I equals 2, so I'll put a 2 there. I'll output a 2, and then I'll put a plus because I'm in my break mode. And then it goes on and on until the last iteration, which in this case will be 5. So we have 1 plus 2 plus 3 plus 4 plus 5. And I encourage you to try representing the sums of sum all the way to 20 and or a general number in any case in this way. And connect this formula and this summation notation as it's stated. So that's just a fancy way of talking about this specific notation that we're writing here. But so why is this so useful? Well, for one, we can shorten down like how long we're taking to write all of these. But you can also do different things. So I'll just write a quick sigma over here. And let's start at 1 again. And let's end at an arbitrary number, let's say 10. So what are the different things you can do for this? Well, you can also try anything. You can try I squared. Let's try I squared. With I squared, you still do the same iteration process just to get a feel for it until you truly understand what is happening. So let's start with just an iteration method. So first we take our input. So we have I, right? And it's on its first run. So this is the first round. So we have I is equal to 1. So then we put our 1 into here and we get 1 squared. So our output would just be 1. We then have to put a plus because it's in the break mode. So now it goes on to the next iteration. So we have I equals 2 and we have put the input in here. So 2 squared is equal to 4. And I think may see where this is going now. Because then when we put I equals 3, because remember, we're going all the integers, the positive integers from 1 to 10 inclusive. So we're going I equals 3 now. So 3 squared, and we have 1 plus 4 plus 9. And as you can see, this is much easier to write than writing out all the perfect squares from 1 to 100. So yeah, this is going to keep on continuing with not any clear arithmetic pattern, but I'll put this dots anyway. It's the sum of all of the perfect squares. And this will go on until 9 squared, which is 81, and 10 squared, which is 100. So I hope you found this interesting. We first looked at the way we can figure out a sum of the numbers of the positive integers from 1 to some value n, which is 20 in this case. And we derived a formula from that based on a creative way of multiplying this by 2, by switching it around and adding each term to the opposite end. So that was a very creative way to figure out this formula. And we also learned, well, how is there a faster way I can write these sums, because they take a pretty long time to write. So in that case, we can use this summation notation, which is very useful. So I hope you enjoyed this lesson, and thank you.